Go to the screen. Still not full screen on Zoom. You need to swap.
Maybe share the other screen on Zoom.
You go here. Swap. What is it? Yeah, I'm not sure. Spanish. No. It's good.
No.
I think. I don't remember which one. We need to click on this one or the next one, and then select to be swap present view. Yes, this one. Okay. And now we see that. Okay. So go out from Zoom. Go out from screen sharing, and then first open full screen on your laptop, and then share that screen. I need to swap again.
It's a bit complicated, but
Yeah.
is it now?
And now share on Zoom on that full screen. It is good. Yeah. Okay, so good afternoon, everyone. I'm Mikel.
My main goal is to tell you what I did. First of all,
Yes. Is someone not muted? I think
No, the owl died and the rest of it.
Okay.
okay. So first of all, I'm coming from the city of Pamplona, which is located in Navarra, in the north of Spain, on the border with France, and it's well known for the festival called San Fermin in Europe. So basically, I did all my academic life there. So I did the industrial engineering bachelor, and I did a master's in applied and computational mechanical engineering, and then I started the PhD at the applied and computational mechanical engineering group. So in this group, we basically do modeling, simulation, identification, and optimization of different mechanical devices. Also, there are some other research staff which are working on structural analysis. We have been also working in mechanical vibration. Where on the left we have a recent work in solar panels, characterizing them with an analysis. Also, we have been working in wind turbines and robotics, so quite multidisciplinary, but always focusing on modeling. So, during my PhD, the idea was to start using data-driven science for some tasks that we think it could be beneficial for us. So we first started with reduced order modeling in wind turbine blades. I will give you a little hint about this, but right now this research line is quite paused, and I'm working more on the hybrid modeling task. So the hybrid modeling task was originally developed to overcome an issue we have with this small device, which is an energy harvester that I will tell you a little bit about later. But basically, the problem was that there's a magnetic interaction, which is difficult to. So here is where we decided to combine our physical knowledge with some matching. Okay, so as I told you, I will start with wind turbine blade modeling. Till now, with the smaller blades, the simulation programs, usually with one or two modes per blade was enough to model those blades. But right now with those really long blades, it's more accentuated nonlinearity, so finite element models are becoming more and more popular, which go to thousands of degrees of freedom. And to overcome the European code, you need to conduct a lot of simulations, so the computational cost is too. So our idea was to kind of obtain reduced order models to prove that data limits. So we basically thought about using a simple methodology, it's dynamic mode decomposition, which basically uses data to do a spatial temporal decomposition and obtain reduced order. So basically what we do, okay, so on the left, basically data is collected, then we have two time shifted matrices, basically matrix X prime is shifted, so we can relation those through that state transition matrix A. And then we have our regression problem, which is solved with the pseudo inverse. And here, depending on how many singular values we use on that SDD decomposition, we can get a reduced order model with different sets. So that was our idea. We have also other variations of this algorithm. We have DMD with control, where we try also to estimate a B matrix to account for that external input. Extended DMD, where basically on that data collection, we also use a dictionary of functions to account for nonlinearities, and higher order DMD, which uses time delay embedding to use several instances to predict the next.
Maybe for those who are following system identification methods more from the structural side, I could say that DMD at the end of the day is not so different to subspace identification methods. It creates again a Hankel matrix of the delayed inputs. It's very similar conceptually. More of a linear construct with respect to the, I guess, relation to the observations, but they have a very simple thing.
Okay, so since our idea was to use this on nonlinear problems, we started with a numerical example, the most simplified wind turbine blade, let's say, which is a cantilever beam with geometric nonlinearities, and in this case, we were using a really low jump modulus in order to get really high deformations. And we tried with cases with arbitrary initial conditions, external loss, different cases. So here, if we compare the linear behavior in blue and the nonlinear in orange, we can see that the displacement of the freedom node, we can see that it's completely different. And if we look at the deformation of the blade, it's also completely different. So in theory, a linear model won't make any sense. But we first tried with this DMD methodology. So it's very simple. We use finite element modeling. We simulate the model, we collect those data matrices. The last one is with the external inputs. So depending if we use it or not, we get a reduced order model, which has the possibility of using external inputs or not. And then we validate the different models and use them for simulation. So using DMD here all the time, in blue will be the simulated data, and in orange the model. We can see that if we use more singular values, we get a better model. But in this case, we could capture the dynamics on the y-axis, but on the x-axis, since it's more nonlinear, we couldn't capture it. So that's why we jumped to higher order beam. And in this case, we got a massive overfitting, and basically the model was only usable for this case. So if we change slightly the initial conditions, it won't work. Okay. Obviously, DMD with an external load is problematic since we don't have that B matrix or we are not estimating it. And using a lot of similar values, we could get a decent result, but on that day matrix, unstable poles were appearing. You can see there are red, so the models were basically unusable. Higher order DMD again is able to capture the dynamics, but again we have a massive overfit, and we don't have any possibility, since we don't have a B matrix, to use in all plot cases. With the NDB control, we solve some problems, but again, we are not able to capture the nonlinearity on the x-axis. So we decided to add control to higher order DMD, and also to add those dictionary functions from the extended DMD. But still, even if we were able to fit the data, we got a clear overfit, since changing introducing the sliders change on external load, we could then validate the model. So basically, the only use of all of this is maybe using it as a surrogate model. So adjusting the model with the first couple of seconds, and then if the external load case and everything is exactly the same, could work. But honestly, this led us to pause this part of the simulation and go to another task, since it wasn't good. So as I told you, it's quick and fast, but it either underfits or overfits the data. So going into hybrid modeling, this is a completely different task, but we will also use data-driven models. So usually when we have a mechanical device, we would like to have a mathematical model. So in this case, for example, this is position, velocity, and acceleration as input. And then we estimate the external output that we are getting. But as I told you, in the energy harvesting device, in some cases, some parts of the model may be unknown or unknown. So that's where we decided to introduce, in this case, a machine learning algorithm, a neural network, or something else. So here is hybrid modeling. So as I told you, all this came from this problem, which is the modeling of an energy harvesting device. This small device has more or less the size, like 10 centimeters, and you can take it with your hands. It's intended to be located in the nozzle of the wind turbines, and the idea is that it uses the vibration energy of the nozzle to obtain a small voltage, which will feed an autonomous node, which is thought for wind turbine monitoring. So basically, it will feed all the accelerometers and even the post-processing part. So this small device has two parts. So we have the other part is basically a stator, which has some points, and the inner part are three blades with some magnetic magnets. Okay. So when the wind turbine vibrates, these three blades are moving, and they create a variation in the magnetic field, which induces a voltage in the coils of the state. We get a small amount of energy, but this is enough usually to fit those small sensors. And as you can see here, we have this is the testing platform we developed, and then for the identification of the system, what we are doing is using a mobile phone, and we will get the position of those three stickers to estimate, which is the angular position of the blades. Okay. So as I told you, the harvester has three blades. The magnets are in half configuration, which is important from the electrical side of view, and we have 24 coils. This also was adjusted by the guys which are working on the electrical side. As I told you, we have the three blades and the stator with the magnetic coils. So coming into the modeling, to the dynamics, you think about this system is basically a system composed of three pendulums, but those three pendulums have an interaction between them, which is magnetical and is quite difficult to model. So we have 5 terms for the equation. We have the inertial term, the mechanical loss term, electrical generation term, which depends on the resistor connected to the coils. This will make it the system more damped or less, and the energy output different. This has to be adjusted as well. We have the term for the magnetic interaction, and the external excitation, which is basically the vibrations of the mass. And here, as you can see, right there on the left, we have that magnetic interaction, which only depends on the positions of the blades. We also have the electrical part, which is a model depending on that electrical generation term, and we can get the power output of the device with this. And as you can see, the models are linear in the parameters, so we have always something multiplying the parameters, and this is really positive, since we can then use least squares to solve the identification problem. So as I told you, modeling the magnetical part is especially complicated. And first we started with a Voigt's model, which was based on a simplification of magnetical dipoles between the different plates, which is this one. Depends only on the positions of the blades. And we have here this term, which is the potential energy, and then it's derived, and we get the value of this term. What is the problem here? That we only have one term in red, which means this model is not too flexible. Okay, so it's quite complicated to adjust it to the data. As I told you, what we first did, which was write equations in a linear equation. We can also do it for different load resistors, since we write different combinations, and then solve this problem by least squares. Okay, so now we need the data. So the data is obtained with this setup here, where we have the harvesting device with number 1, then we have the platform. We can adjust the excitation, and then we have the data acquisition through the mobile phone, which is high frequency video. We also have an accelerometer in the platform, and we can also measure the voltage and power generated at each of the coils. And then we synchronize all those 3 measurements with an LED light, which is attached to the platform, and it appears on the video recording. So, targeting all the data, we do first image processing to get the positions of the blades, but also the first and second derivatives. So first, we identify where in the video they appear, those center of gravities of the stickers. We fit a circle, we get the center of the circle, and then with arctangent method, we can get the positions, the blades, and then we do Tikhonov regularization to smooth all the signals and get the derivatives. So basically, we have access to the whole state of the system, which is really helpful for system identification. So then, since we have 2 experiments, we use 2 for training and 1 for validation. We get those estimated parameters, and then we do the validation. So as I told you, the model is not flexible enough. We have the measurements in black. On top are the the torques, and right down here is the generated power, and in red we have the our mode. So as you can see, we didn't get a good fit, and also it was difficult because as you can see, the data is quite noisy. The data on top is coming from the accelerometer, and also the platform was not going well, so the data was quite noisy, making it even. So here we decided to jump into a black box model for the magnetic term estimation. So basically, we combine the physics which depend on those parameters theta, the last one, and a neural network which depends on the parameters phi, and we put all together and get a hybrid model. So we have those known terms plus the unknown terms. In this case is that the function is the one with the unknown terms, and it's basically a feed-forward neural network, really simple one. And in the case of the harvester, of course, the magnetic term is the one that will be modeled with the neural network. And in this case, since we know that this interaction only depends on the positions of the blades, we will only use them as the input to the neural net. And then, as you can see, we have the three physical parameters, and we will also estimate their values. We have a loss function. In this case, we use the torque measurements and their difference with respect to what we get from the model. And since we have the power output model, we can also use it in the loss function. And after all the optimization process, we get a model, static model, and also the values of the physical parameters. When it comes to validation, yes, as you can see, we have really noisy data from the measurements. As I told you, the platform when it reaches the end of the platform and changes direction, there's like an overshoot. So the measurements are quite noisy, but our predictions with the hybrid model were way better than what we were getting before. And also, if we have a look at the generated power prediction with our model, in this case, the measurements are also in orange and the prediction in blue. You can see that we got a much better result. So with this model, then our idea was to try different configurations and see with which configuration we could get a good results in terms of energy output, but also we couldn't go huge in size. So there's limited space to get the energy harvested in the NASA. So what we did was rearrange all the blocks from our model, and now, as you can see, the output will be the acceleration. Since now we can get the acceleration, we can use numerical integration, normal numerical integration, and we can predict which energy output we will get with any signal. Okay. And this is really interesting. As I told you, we can, for example, some of our experiments were trying to duplicate the inertia of the blades and see which power output were we getting. In fact, there have been more prototypes of this device, and now we are using more inertia on those blades with other materials in order to get a better energy output. And it's a little bit again the model we arranged. So we did here some numerical examples to see if the model was correct, at least empirically. So first, here we try to put the blades out of their equilibrium position, and then you simulate this without any external load. And as you can see, they all go back to the equilibrium position. There's a bit of power generation of the beginning, and then everything goes to zero. And here we tried with a similar signal to the ones that we were using in the platform, and we saw that the generated power value was really close to what we were getting on the platform, which is a few milliwatts, but it should be enough to fit those small sensors. We can also linearize the system using automatic differentiation, and this is also interesting to see if the system is stable or unstable, or how it works if we want to do any changes. So here in this case, for example, the electrical friction is really high, since if you want to get obviously energy output, you need to take it. So basically, it's that friction is really high, the electrical one. So we have a pole, a real pole, really close to the origin. So then the system is working as an overdamped system. Here it's a simple experiment with a linear and non-linear model. As you can see, it doesn't do any harmonic oscillation, so it's clearly overdamped as expected. If we try to move the blades by hand, for example, we could also see that it was really over. So as a conclusion, here with hybrid modeling, we are combining physics and a neural network for the unknown part. We are using some physically based constraints. We can estimate the values of those physical parameters, and we can modify them for device optimization. And we can also simulate the model in time and linearize. So basically, we got a tool to optimize this real world mechanical devices. And then coming here into the end, with the future of the PhD work, the main idea is applying this methodology to other problems that we have in mind, maybe to some problems here at ETH. Quantifying model uncertainty, and then uncertainty in the estimated parameters as well, and also obtaining accurate models when full state measurements are not available, which will be the case, for example, in a structure where we are only measuring accelerations. And finally, it's not completely clear yet, I guess, but my research here at ETH Zurich will be maybe trying my methodology in some structures or some problems here, and also trying other algorithms in this device. And also here last week, we were discussing a little bit here about adding some physical information to the neural extended Kalman filter methodology that was developed here. Basically, this methodology is a Kalman filter, but the transition and observation models are based on neural networks. So the idea is to introduce here some physical information to these two models, maybe obtain better results. So thank you.
Thank you very much. We'll stop the recording now, because then we can post it as a piece on YouTube channel. It's a good example of what a presentation for a new member or a guest should look like, because you gave a good overview of your activities and what you intend to do. Maybe I open the floor for questions to the members first.
Yeah, I have a
Go ahead.
question. Thank you for your presentation. I have a so for example, if the structure system you have some missing physics, you cannot have an exactly form of this physics. How do you combine this in your neural network, in your framework? So how do you identify this problem?
The idea is to use the knowledge that we have.
Mhm.
Anything is positive, and then model the rest with a neural network and or other architecture. And basically use anything. In this case, since it's a really small device with just 3 degrees of freedom, It was basically a multi-layer perceptor with 2 layer universe, something like that, a really small one. But maybe in the structures that we have a lot more degrees of freedom, we will need to use other machine learning algorithms, or maybe something more powerful, more flexible.
Maybe to explain, in this case, you infer a fitted function, a neural network, to represent your system or the part you don't know about the system. But you're also interested in an analytical expression, obviously, that could approximate the behavior.
Yes.
So that you can have an engineering intuition on what is the mechanism.
Eleni.
Yeah.
I seem unable to stop the recording. I think you need to.
Me, but I'm not.